Alright, so part one of this problem, or part two of this problem now, we're going to be coding this, coding problem 1.17. And so in order to start coding, we need to first import our libraries and solvers. So the first, library solver we're going to import is import numpy as np. And so what this does is allow us to do our calculations at a faster rate throughout our program. And then we're going to also use the SciPy library. So from SciPy, we're going to use the optimize module OP, and we're going to import root. And what this allows us to do is from the SciPy library in the optimize module, there's a root solver, and that root solver allows us to solve the roots for a set of equations. Then also from the SciPy library, we're going to look at the integrate module, and we're going to be importing solve IVP. And so what this function does is allows us to solve IVP, which helps us get to the answer for this problem, considering we have differential equations. And then also, we're going to be graphing our answers later on. So we're going to be using the Plotly library, and we're going to be using the subplots module, and we're going to be importing make subplots. And what this allows us to do is it allows us to just create graphs. It helps in the process of the creation of graphs and creation of subplots. And lastly, we're going to be importing again from the Plotly library, so Plotly, and we're going to be looking at the graph objects, and we're going to import that as GL, so we're going to abbreviate it as GL. And so what the graph objects allows us to do is allows us to just choose different types of graphs we want to create. In this case, we will be using scatter plots. So let's just run that just to make sure and we had no errors, so we can move on to the next step. And our next step is to define all of the given data to us. So I've quickly already gone through and typed out all of the given variables off camera, and D1, 2, 1, 3, and 2, 3 are all Stefan Maxwell coefficients, which were given to us. And we changed the units to meters squared per second. Then we were also given a pressure in kilopascals, but we converted that to pascals. So now it's 99.4 times 10 to the third pascals. And then our temperature is 328.5 Kelvin. And then our ideal gas constant is going to be 8.314 joules divided by moles times Kelvin. Our delta, which is kind of like how long the tube is going to be 0.24 meters. And we were not given any concentration, so we're supposed to calculate that. And the way we calculated that is by dividing the pressure by the ideal gas constant times the temperature. And the units for that will be moles divided by meters cubed. And then F12, F13, and F23 are all variables that we created during our scaling process for this problem. And what we were mainly trying to do here was make sure that the denominators were the same between all three variables. And all three variables have the same units, which are moles divided by meters squared per second. And Y1I and Y2I are the initial mole fractions for acetone and methanol respectively. And then N1I and N2I are initial gas 1 and 2, which we got from the scaling process. So now let's just double check. Everything's good to go. There are no errors there. And now we can actually start coding this problem. So we're going to just redefine N1I and N2I as N1. So N1 equals N1I. And then N2 equals N2I. And what that basically is saying is that N1 stands for the molar flux of acetone, and N2 stands for the molar flux of methanol. And so now we're going to define a function dy with the independent variable eta and the dependent variable as the mass fraction. And what this this function dy will do is it's going to serve as our as our solver. So it's gonna be solving for our driving force. So after we have defined n1 and n2, after we have written down n1 and n2, we're going to now define our function dy, and our independent variable is going to be eta, and our dependent variable is going to be the mole fraction, which stands for y. And basically what this function is going to be doing is going to be solving for our driving force. So now we're going to say y1 equals y0, y2 equals y1, and y3 equals 1 minus y2 minus y1. And so what y1, 2, and 3 stand for are the mole fractions of acetone, methanol, and air, respectively. So now, since we have all those defined, we're able to now return a NumPy array with our differential equations. So we're able to say return np.array, and inside this array we're going to have two differential equations. The first one is going to be y1 times n2 minus y1 times n2 minus y2 times n1 goes that divided by f of 1, 2, and then subtract that by y3 times n1 divided by f of 1, 3. And so what this is the mole fraction, the mole fraction of acetone times the molar flux of methanol. The product of that is going to be subtracted by the product of the mole fraction of methanol times the molar flux of acetone. And that's all going to be divided by F12, which is defined which was created when we were again scaling the problem. So then all that's going to be subtracted by the mole fraction of air times the molar flux of acetone divided by F of 1,3. And so for our second equation, we're going to basically rearrange it so that wherever there was a 1, we're going to put a 2, and wherever a 2 is, there's going to be a 1. And what that does is that it just flips where the where acetone and methanol are within the problem. And so what we can say now is y2 times n1 minus y1 times n2 f of 1, 2. And then we're going to subtract y3 times n2 and divide that by f of 1, 3. And so those are two differential equations. And so after we have that array settled, let's just double check and make sure that there's no issues. There are no issues thus far. And we want to see, we're expecting that the mole fractions, or the mole fluxes for acetone and methanol will be going to 0 as we approach 1, as eta approaches 1. So what we're going to do here is going to be using the initial value problem solver. So we're going to do res equals sol IVP, and we're going to say our function is going to be dy. Our time span is going to be from 0 to 1 because that's the range for eta, as well as that's going to be the range for our answers. Our initial values are going to be y and y2i. Our method is going to be equal to redo. And we're using this method because our professor has told us to specifically use this method. And our dense output is going to be equal to true. Now let's just double check there's no issues with that. No issues so far. So now we can return res.sol1. Let's just double check there, and then now we're just going to add a new line code to see if we could get the array out. And here we have shown that both the molar fluxes for acetone and methanol are the molar flux for acetone and methanol are both very, very close to 0. So now we're going to use the root solver to find the exact values of the molar fluxes, molar fluxes of acetone and methanol. Since in the beginning here we used our initial guesses. So what we're going to do is we're going to define another function, f of n, and what that's going to do is it's going to be our root solver. So we're going to say n1 equals n0 and n2 equals n1. And basically these are where the molar fluxes for acetone and methanol are going to be stored. So now, since we have that, let's just shift everything over to make sure that everything, like the whole driving force function, is nested within the root solving function. And let's just solve that. And now we're going to test if our function works, if f of n works. So f n is going to be n1 and 2i. Let's just run that. So there's an issue. There's no float attribute to n2i. I think I messed up here. Okay, so there are no errors, meaning that it is there are no errors, meaning that the whole function is working properly. So now what we're going to do is actually solve for the roots. So we're going to say res x equals root, and our function is going to be f, and then our x naughts are going to be n1i and 2i. And let's just see if there's any issues with that. So we found that there's a mismatch between the function arguments here. So let's just move these aside. And let's run this again. So it solves perfectly fine. So now we can do res x. Okay. So now what this is showing us is that our solution has converged. Our message shows that our solution is converged, which is good, and our success is true. That's also a good sign. And all the way at the bottom here is x, the x array. And what these are the exact molar fluxes for acetone and methanol. So what we're now going to do is that we're going to be extracting those and putting those into an array. So now what we're going to do is just say res n1 equals res x, and then we're going to put brackets of 0. And that's going to be for the molar flux of acetone, and then n2 equals res x, and that's going to be the molar flux of methanol. So we're going to x out of here, and then we're going to go ahead and copy and paste our driving force function right down here. And now let's see if it runs properly. And we have an indentation issue. So let's push this back here. Let's see if that fixes the issue. that. Oh, that just portrayed the array. Okay. So now we have solved our issue here, and now we can tell that there are no more errors. There are no errors popping out. So now what we can do, since we have a root solver in place, is that we can go ahead and now graph our solution. Since now we have our functions defined and they both work, we can go ahead and start creating the eta plot. So the eta plot is going to be created by using the linspace function, and we're going to have 50 points, which are going to be stored in an array. So we're going to say eta underscore plot equals numpy.linspace, and we're going to say the start is 0 and just 1, and then we're going to put 50 as the number, and then we're just going to make sure that there are no errors. And so the start and end points 0 and 1 are used because that's the range for eta, 0 and 1, and then 50 is used as a number because we want 50 points. So now what we're going to do is use res sol eta underscore plot. And let's see if that outputs the array, which it does. So what we did was call out the array so that we could see all the values to make sure that everything is running smoothly. And now we're going to hide this by saying that sol equals the array. Now what we're going to do is actually go ahead and define figure. So we're going to say fig equals make underscore subplots. So this allows us to create a plot, and we leave our parentheses blank because we want we only want one row and one column, and that's already default, so we don't really have to mess with anything without the parentheses there. And now we can say fig add trace graphing objects scatter and then x is going to be equal to eta plot times delta, and then y is going to be equal to our sol of 0, and our name is going to be equal to and let's just double check if that works, and that produces our acetone graph. So what we're going to do now is just copy and paste this twice. I'm going to change this to 1 and methanol. And what we're going to do here is that the y for error is going to be equal to 1 minus sol of 0 minus the sol of 1. And let's just run that real quickly. And now we have our final answer, which is this graph. And we can see that error is approaching 1, while methanol and acetone are approaching 0 as eta approaches 1. Or not eta approaches 1, but as the x-axis continues on, which is eta plot times delta. And that is our solution.